So I wanted to talk to you a little bit about some of our explorations in trying to design some tremendously difficult missions to Saturn's moon, Titan. Let's sort of back up a little bit. Here's a beautiful portrait of Saturn and Titan. This one's from Cassini. I have to point out this is a little bit misleading. In this picture, Titan is a lot closer to the camera than Saturn is. Titan is a big moon, but it's not actually almost as big as Saturn. So Titan's in the foreground, Saturn's in the background. Nice picture because it's almost true color. Saturn is actually a very yellow planet. I'm sure many of you have gone out and watched Titan. Well, you can actually see Titan in a moderately sized telescope and seen Saturn. Saturn is sort of the yellowish planet, and Titan is actually a sort of ruddy orangish yellow color. Well, Titan was actually discovered by Christian Huygens back in 1665, the first moon of Saturn to be discovered and the largest. Here's Christian Huygens. The guy was a rock star. I mean, take a look at him. He's a rock star. He was amazing. In addition to discovering Titan, thought to be the largest moon in the solar system, he was the first person to explain centrifugal force. He invented the wave theory of light, and he invented the pendulum clock, among other things. And he was also the first astronomer to realize, hey, the funny little shape of Saturn is because it's a planet with rings. He literally discovered the rings of Saturn. I mean, how cool is that? That's an amazing guy. So they named the moon Titan because Saturn is, of course, the king of the Titans, who predated the Greek gods. And Titan is just the name of the Greek gods, but also because it's the largest of the moons in the solar system, or so they thought at the time. Turns out that orange color of Titan is due to aerosols in that thick atmosphere. So Titan looks bigger than it is because it's shrouded by hundreds of miles, actually, of a very thick atmosphere. The only moon in the solar system that has a really noticeable atmosphere. So here's the rocky planets and moons. So Titan, in fact, is slightly smaller than Ganymede. Ganymede takes over the title of the largest moon in the solar system. But these are big bodies. They're almost as big as Mars, bigger than Mercury. So these are moons that are as large as planets, Ganymede and Titan. So it's not merely a moon, but it's pretty much a world in its own right. Again, the only moon in the solar system with a noticeable atmosphere. And here you can see a sort of interesting view, kind of looking edgewise through the atmosphere. You can see that haze. In this case, you're looking at the scattered light off of the haze, but the haze is actually that yellowish, orangish color. And I'll talk a lot more about that in a moment. Well, so the first close-up looks at Titan were from a flyby mission, the Pioneer 11 spacecraft, then the Voyager 1 spacecraft in 1980. But we got our best view of Titan and Saturn when the Cassini Saturn orbiter arrived at Saturn in 2004. And it carried the European landing probe Huygens. Something to note is that haze in the atmosphere is opaque to visible light, so you can't see the surface from a telescope in visible light. It's somewhat transparent to infrared light, so you get a hazy view through the haze in infrared. And here's sort of a fascinating image of Titan. This is Titan that's almost between us and the sun. So we're looking at the sunlight coming in at a grazing angle. And right there at the limb of the planet, you see this reflection. So we can see there's something big and flat and reflective that we're looking at. Well, turns out that's a sea or an ocean. We can look through the haze. It's a hazy view because that atmosphere scatters light, but with infrared we can look through and we can see now the features, these lakes, or you could call them seas, of Titan, the Titan seas.
Is that
Well,
H2O?
Mention that in a second. Titan, but I'll give you a hint. Titan's average temperature is 92 degrees Kelvin. So, so there's the radar image of one of these giant seas or lakes. This one's Ligeia Mare, the second largest body, but this particular one is as big as Lake Huron and Lake Michigan combined. So these are not little bitty puddles. These are giant lakes. But so there's the environment of Titan, answering the question, what are these liquid bodies on the surface? And other than Earth, Titan is the only place in the solar system that we see bodies of liquid on the surface. On Mars, we see places where liquid has been, but we've never actually caught liquid on the surface of Mars. But Titan, we see at many, many places. But at an average temperature of 90.6 Kelvin, maximum temperature of 93 Kelvin, well, that's not quite 200 degrees below zero. That's way too cold to be liquid water. So these seas actually are not oceans of water, but they're seas of liquid methane, covering a surface area of almost 500,000 square kilometers.
Well, when does methane freeze?
Methane freezes a little bit below this, but yeah, methane stays liquid pretty cold. It's what we call a soft cryogen. So you don't have to take it all the way down to liquid hydrogen temperatures of a few kelvins, but it freezes a little bit around, somewhere around liquid nitrogen temperature, a little bit below. Depends on pressure, by the way. And Titan is also a slightly higher atmospheric pressure than the Earth. Here's an artist's conception I kind of like. You probably wouldn't be able to see Titan's, through Titan's atmosphere to look at Saturn in the distance like that, but it's kind of pretty to think so. Well, I mentioned Cassini carried the European Huygens lander, which actually parachuted in through the atmosphere, dropped its heat shield, and made a soft landing on the surface. That was sort of an amazing mission and would be certainly worthy of an hour or maybe a 2-hour talk, just the complexity of the Huygens lander. But a beautiful thing about it is that it took images as it came down. Here's the side-looking images from above the clouds. You can see that,
What year?
that haze. And then down to so it's 2005. So, and then down, looking through that haze at some of the features on the surface. The view straight down as it came in, here's a mosaic of 3 images looking down. And now you can see Titan not only has this liquid on the surface, the liquid methane, but it also has a hydrological cycle, like the Earth, of methane evaporating, forming methane clouds, and then precipitating down. And you can see what appears to be actual rivers that are feeding these hydrocarbon lakes on the surface. Well, made it to the surface. Hooray, here we are. This is the view from the surface by the Huygens lander. It had a pretty decent camera. Unfortunately, the camera didn't have a pan on it, so it took just one image. It actually took, I think, 100 images, but they were all pointed exactly the same way, so they show pretty much the same thing. Here it is with a little bit of sharpness added. So computer enhancing to bring out the sharpness. And if you want to know kind of how big that image, just for comparison, here's a view of the moon, a little bit smaller than Titan, but similar size, and you can see the size of these pebbles compared to a footprint. So these pebbles are an inch or so across. But you can actually see they're very rounded pebbles, very unlike, say, the rocks you see on the moon, presumably rounded because they've been tumbling in the liquid methane. The chances are almost certain, by the way, that these rocks that you're looking at here, the little pebbles, are actually made of water ice. Because, of course, when your average temperature is almost 200 below zero, water is just another form of rock. Another interesting thing about Titan, which I won't really go into great detail, is that it seems to have an ocean underneath the ice. This turns out to be very common in most of the icy outer moons of the solar system. Pretty much everything that's orbiting a primary enough that it has tides that give it a little stretching and compressing that adds heat. But if you were to be able to look below the surface of Titan, you'd discover there's this very thin ocean underneath the ice shell and before you get down to the icy and then rocky core of Titan. Now I have to think it's sort of interesting. We know there's ice on Titan. We know there's hydrocarbons. I'm thinking, well, so what is this ocean made of? Well, most people think it's probably a mixture of ammonia and water that keeps it liquid even at relatively low temperatures. But I can't help but thinking with carbon compounds and with water, the other alternative for what's in these oceans is going to be alcohols. So I think there's a finite chance that that ocean underneath Titan's shell is made out of vodka. Have to just keep that in mind. Well, everybody's fascinated by Titan, and there is a NASA mission going to Titan. It's being put together by our colleagues at the Johns Hopkins Applied Physics Laboratories out in Maryland. If everything goes right, it'll launch in July of 2028. It's the Dragonfly mission. Most of you are familiar with the Ingenuity helicopter, I hope, the first vehicle to actually do atmospheric flight on another planet. That was about a little bit under a 1 pound helicopter, has a flight duration of 160, 170 seconds, about 3 minutes, and has flown, well, hundreds of meters on a single flight. Well, Dragonfly does a little better than that. This isn't merely a test of flying on Titan. This is actually a full-scale rover mission that happens to fly. So this is, I'll let the Johns Hopkins people sort of show off the. Oh, well, okay. They don't want us to see it. Huh. Okay.
Psychedelic.
Let's try that again. I don't know why Microsoft suddenly decides to quit sometimes. Where was I? Here we go. See if this will go. Cross your fingers. So there's Titan, viewed in the infrared, of course. You can't see the features through the atmosphere. So like all missions, comes in on a heat shield, brushes off the interplanetary velocity against the atmosphere, pops a pair of parachutes, first a drogue parachute, opens up a main parachute. Much similar to Huygens or any of the previous missions, but unlike the other missions, it doesn't land. You drop it out, and Dragonfly is an octocopter. It has 8 rotors that allow it to fly. And this is as big as this table. These are big rovers, and as heavy as the Curiosity rover. So this is a serious scientific mission. It actually has the flight plan that it finds a nice, safe landing spot. Then for the next landing spot, it flies over, surveys it from the ground, comes back. Then the scientists on the ground check out, make sure that everything's safe about the new landing site. The next time it goes over, surveys the landing site after next, and lands and sort of leapfrogs around with the capability of, let's see, I think about 10 miles, maybe 5 miles per flight. So this is a extremely capable rover that will tell us a lot about the fascinating features of Titan.
What's their power source?
This one is a multi-mission radioisotope thermoelectric generator. So it has basically a number of small pellets of plutonium oxide, basically a ceramic form of plutonium that, of course, stays hot from basically fission, spontaneous fission, and I think it's actually spontaneous alpha emission. And then we use thermoelectric generators, essentially like the thermostat on your house, that produce a little bit of voltage out of a heat difference between hot and cold.
How long is that thing?
So, radioisotope thermoelectric generators have a pretty good history of operation in space. The Voyager missions, launched in the late 1970s, are still producing power, and they are RTG. This is a different version of the radioisotope thermoelectric generator. This particular Voyager was designed only for vacuum. So if you landed it on Titan, it wouldn't produce any power because the atmosphere would short circuit the thermal system. But MMRTGs are designed to be used even in atmosphere. So if everything works well, they'll last for decades and decades.
So I get one of those for my electric vehicle? And I don't ever have to fill it up?
You could do that. They're about 300 watts. Your electric vehicle is a couple of kilowatt hours per mile, so you won't be moving very fast.
Maybe a scooter,
And
just a scooter.
Yeah, the Alpha might be a problem.
it'll cost you maybe $20 million.
Oh, well,
Is that a problem? You could take a loan.
What was the atmosphere?
The atmosphere is mostly nitrogen with a saturated trace component of methane. That's sort of an interesting story. Back in the telescope era, when the scientists were looking at Titan with telescopes, trying to learn what they could about it, they of course did spectroscopy, and they looked at the spectrum of Titan and they said, aha, methane. Because of course you can't see nitrogen when you look through the Earth's atmosphere. Because when you see nitrogen, you say, well, duh, you're just looking through 7 miles of nitrogen atmosphere when you look from Earth. So they didn't know about the nitrogen. All they knew about until the spacecraft missions got there was that it had methane in it. Plus, of course, it has these aerosols that give it that kind of brownish, yellowish, orange color, which I'll talk about in a second. But what I really wanted to talk to you about is that at NASA Glenn, we have an engineering team who is tasked at looking at advanced concepts. So we develop technology for spacecraft at NASA Glenn, and the Compass team looks at what we can do with the advanced technologies that we're developing in the way of future missions that can't be done with current technologies. So with that said, let's take a look a little bit more of those seas of Titan. Kraken Mare, Ligeia Mare, and Pungia Mare. Well, what's under these Titan seas? So supported by the NASA Innovative Advanced Concepts program, we said, let's design a submarine for under the oceans of Titan. So we'll send Dragonfly later this decade to look at what's above the surface of Titan. Let's look at what's below the surface of these seas of Titan. So here's our animation of the first phase of the mission. This is phase 1 of our Titan submarine study. For phase 1, we decided, in order to lower the cost of the mission, we'll have it communicate directly to Earth. So you notice a big fin on the back of the submarine. That's actually the radio antenna, the phased array radio antenna needed to send a signal all the way to the Earth. So we can submerge under the Titan methane. It has sonar, just like a submarine. But we also are going to have a light so we can illuminate the bottom and look and see visually what's there. Swim around and find the interesting features on the bottom, look at them, and do various spectral analysis of the bottom to find out what is underneath the surface of these oceans. Actually, there were some interesting problems in designing the Titan submarine. When we first started the design, we said, oh, it'll be just like a Earth submarine. When we want to go up to the surface, we have compressed atmosphere. We'll just blow the tanks and we'll float up to the surface. Turns out the atmosphere of Titan is mostly nitrogen. If we blow the tanks when we're deep underneath the surface, turns out at high pressure, nitrogen is soluble in methane. So instead of blowing the tanks, we just saturate it with nitrogen. So we had to come up with an alternative method to surface, and we ended up using, I believe, neon, a noble gas that is not liquid at nitrogen temperatures. But here's the...
So would that mean there's going to be a limit of dives possible?
We ended up actually having a closed system. So essentially there is a bladder that we now fill with the noble gas in order to rise. But yeah, we couldn't afford to blow it off into the atmosphere because it would limit our lifetime pretty quickly. And why is that not moving to the next one? Come on. Huh. Okay. Oh, Microsoft doesn't like me today. Huh. Grab something else. And,
so does phase one need their additional
yes, I want to
submarines
show
planned?
you the phase two.
Well, I understand. Thought maybe you could vamp while your
Okay,
fingers
force
do the
quit. Try it
poking.
one more time. Yeah, force quit. Oh, yeah, thank you.
Yay. Those teeth.
So in phase two, we gave up on the idea that we're going to communicate directly to Earth. Turns out communicating billions of miles across space takes a lot of power, it takes the giant antenna. The whole reason that our vehicle was so large, let me show you how large it was, I forgot to show you that. Compared to a standard pirate, but stands about as tall as a 6-foot pirate plus hat, and is actually a little bit over over 5 meters long. So a pretty big vehicle. So we said, well, the reason it was so big turned out to be because we decided to communicate directly back to Earth. So we said, well, let's give up. We'll put a communication satellite in orbit around Titan. Now we only have to communicate with the communication satellite. That allowed us to design a much smaller vehicle. So the phase two design is only 2 meters long, weighs 500 kilograms, and is supported by the orbiter, a much, much smaller vehicle and lower power. So here's a view. Comparing it to, for example, the Curiosity rover on Mars, it's about the same size, a little bit lighter. Curiosity is actually 900 kilograms. The Titan turtle is only 600 kilograms, but comparable size, about 2 meters long, and moves, in fact, a lot faster because now we're swimming through methane. We're not crawling on the surface of Mars. There's the view of the Titan turtle. But where do we go from next? If we can get the Dragonfly, we can do the Titan submarine. What is the next thing we want to do?
I have a question.
Sure.
Do you have any idea how deep those seas are?
We do. We have radar soundings of some of them, but the radar soundings didn't reach the bottom on all of the seas. So I'm trying to remember the depth of the seas we've looked at. They're in the order of a kilometer deep on the deepest
So you know
of the
places
ones
that are
we found.
shallow enough to get to that.
Yeah, yeah.
Is there an expectation for what kind of current might be in the seas?
There are models, but not measurements. There are tides on Titan. Titan keeps one face to Saturn all the time, but nevertheless, the slightly eccentric orbit, slight amount of basically sort of nutation and wandering means that there's a little bit of tides, and that causes the sloshing of the lake from Kraken down to some of the other lakes and back over the course of an orbit. So the estimates suggest that the currents in the Titan seas are less than a meter per second, so pretty gentle currents. But that's all from modeling. We don't have actual measurements of the currents in them. Well, here's that picture of Titan from the surface again. And what you really notice is that it's the other red planet, but unlike Mars, Titan is red due to these compounds called tholins. So tholins are sticky red goo. Carl Sagan gave them that name from the Greek word meaning muddy. And they're basically sort of this muddy, icky stuff, kind of like asphalt, kind of like used motor oil, kind of different from either of those. This seems to be what you get when you expose hydrocarbons like methane with nitrogen, a little bit of trace other elements like perhaps sulfur, to ultraviolet radiation for a few million years, along with cosmic radiation. So you get these polymer, complicated, mostly organic compounds that basically on Earth we would call photochemical smog. But sticky red goo. But those may be the building blocks of life. We see these all over the outer solar system. Titan is just kind of the nearest of the objects that we see these gooey tholin materials. But once you get beyond Saturn and Titan, you see this reddish color all through the solar system, on the surface of asteroids, on the surface of moons. You see it on Pluto and Charon, and further out into the Kuiper belt. They're ubiquitous in the outer solar system. Well, these are compounds that haven't been baked by the sunlight like the Earth, and it's probably material that's very similar to what had been around on the planet Earth early in the solar system. Well, so because of its...
They're not earthbound?
We have not found them on Earth.
You haven't
Because
analyzed them yet?
there's, well, we've made samples of them, of course. Where am I? Here's some, shown in the picture, are some tholins that have been synthesized in the lab by exactly this technique that we're talking about, by taking these hydrocarbons along with perhaps some methane, some ammonia, nitrogen, etc., exposing them to deep vacuum ultraviolet along with cosmic radiation, and just seeing what you get. And you get all of these sort of complicated organics.
Is this sort of in, like in similar to Carl Sagan, did he call something a primordial soup or something like that?
Yeah, I think that was Yuri's name for what was the original material from which life was formed. And this may well be part of the materials that have formed originally into the primordial soup from which life eventually arose. We don't know. We don't know much about them. We've made what we think are tholins that are similar to what's in the outer solar system on Earth, but we don't know for sure because we've never found a sample. We've never brought back a sample from this far out in the solar system. So that is really the ultimate mission we want out of Titan, is we want to bring back a sample from the surface and atmosphere of Titan in order to take them to the very capable labs on the Earth and find out what this material is. Well, first question is, can we even launch off the surface of Titan at all? What is that thick atmosphere? Well, in some ways it's easy, in some ways it's hard. It's easy because the gravity is light on Titan. It's hard because we have 4 times the atmospheric density, and it's 3 times as high an atmosphere. It's a thick atmosphere, not merely thick meaning dense, but thick meaning it extends vertically higher than the Earth's atmosphere because of the low gravity. So we looked at 2 possibilities for getting back a sample from Titan. One is, we said, well, if we can just launch off the surface, we could have another spacecraft come in, grab the sample that we launched, and take it home. That's the plan that's being used for the Mars sample return, which actually is in trouble at the moment because of designing the various spacecraft. Turns out to be a tricky problem. But the other thing we looked at is say, well, maybe we can make a launch vehicle that can launch off the surface of Titan, possibly stop in orbit, and then launch all the way back to Earth without having a second spacecraft that comes in and picks it up. So, well, and actually we picked that as the way to do it for several reasons. But one reason we picked this as a way to get home from the surface of Titan is we said, well, Titan has a lot of resources. Let's make the rocket fuel on Titan. Well, why? Well, the reason is because a launch vehicle of the capability that can go from Titan all the way to the Earth is mostly fuel. Rockets are 90% rocket fuel, and sometimes more than 90%. So if we can make the fuel on Titan, we have to launch a significantly smaller mission to Titan to bring the fuel home. So, well, rocket fuel consists of 2 parts, fuel and oxidizer. I'm sure that you all learned that in your introduction to rocket science class. Fuel is easy. Titan has lakes full of rocket fuel. It has lakes full of methane. And our first thought is, oh, no problem. We just need a pipe and a pump. Stick the pipe and pump it in. But the oxidizer is tough. It turns out that actually methane rocket fuel by weight is mostly oxygen. So the fact that we get the methane free doesn't solve our problem. We need the oxidizer. But fortunately, those rocks are mostly water ice rocks. So if we can scoop up rocks, pulverize them, melt them, electrolyze the water, we can get oxygen. So we have a plan. That would make a methane oxygen rocket. Turns out methane oxygen is great. It's nearly an ideal rocket fuel. It's not quite as good as liquid hydrogen and oxygen, but liquid hydrogen is very difficult to deal with and has about the same density as styrofoam, so you need giant tanks for liquid oxygen. In fact, it's so ideal a rocket fuel that these days there's literally dozens of rocket companies that have said, no, we're giving up other fuels, we're going for liquid methane and oxygen for the future rocket technology. Among them, for example, you might have heard of the SpaceX Starship vehicle, liquid methane, liquid oxygen fueled vehicle. But I just wanted to show some views of, these are some methane oxygen rocket engines we've done testing of at NASA Glenn. I just love that sort of pretty blue flame in the methane rocket engine. Another one being tested in our altitude test stand That's actually the same size as the engine we're going to use on the Titan sample return. So doing the calculations backwards from what it takes to get home, we're making a launch vehicle that's going to end up weighing 3.7 tons on takeoff, but only 470 kilograms of that has to be landed. The rest is rocket fuel that we make on Mars. Turns out it's 750 kilograms of methane and a little bit over 2 tons of liquid oxygen. Turns out methane has much lower density than oxygen, so the tanks are about the same size. We need about 2 cubic meters of liquid methane, a little bit over 2 cubic meters of liquid oxygen. Well, how are we storing liquid methane, liquid oxygen on Titan? Well, Titan actually is helping us out here. It's cold. It's really cold. It's not quite liquid oxygen temperature, but it's also a high pressure environment. So the liquidus temperature of oxygen raises a little bit under pressure. So with only about 1 atmosphere of additional pressure in the tanks, we can keep the oxygen and the methane liquid at Titan temperature with no need for a refrigerator to keep it cool. So turns out, well, Titan helped us out here. It gave us a perfect propellant combination and a perfect storage. Well, going through what we have to produce the methane. As I said, our first idea is we just need to suck it out of the seas of Titan, which are mostly liquid methane. We ended up going to another concept, which actually I have to credit Ralph Lorenz, our collaborator at Applied Physics Laboratory, for coming up with this. He said, well, that turns out to be really complicated. We have to land right on the shore of a sea. We have to have a perfect landing site right on the shore of a sea. The pipes and pups are non-trivial. Instead, the atmosphere is saturated with methane vapor. All we have to do is condense methane out of the atmosphere. Methane serves the same role in the atmosphere of Titan that water does in the atmosphere of Earth. So essentially what he said is we need a dehumidifier for the atmosphere of Titan, and we can just condense liquid methane. That means we can land anywhere on the planet, it doesn't matter where. We can land near the lakes if we want, but we could also land far away in another landing site that might be more interesting. So this is the straightforward way of doing it. We can liquefy the atmosphere either by cooling it or by compressing it. Turns out in our analysis we thought compressing it was a little bit easier. You compress it, it heats up, let it cool down, and the methane liquefies directly out of the atmosphere. Water is a little trickier. We need a rover to go out, scoop up rocks and sand, possibly even drill it if all we can find is bedrock. We have to purify the water. It's going to have all sorts of stuff in it, among other things, these icky tholins we've been talking about. So we're doing that, in fact, by evaporating. So we evaporate the water out, condense it, and then send it to an electrolyzer. Then we're not keeping the hydrogen, we just vent that out, and we save the oxygen, which we then compress and cool and send into the tanks. So there's the propellant plant in scale, showing how big it is compared to an ordinary vacuum cleaner. I could go through some of the details. Are any of you out here chemical engineers? No? Okay, I'll skip the details. Straightforward. Of course, it'll take a while to get the prototype machinery going. Well, how do we land a empty but still pretty big interplanetary capable rocket ship on Titan? Well, turns out it's larger than any of the aeroshells that we've used to go to Mars, or even the Huygens vehicle going to Titan previously. But we have large vehicles that land on Earth. So we picked this particular one, the X-37 vehicle. X-37, in fact, was originally built for NASA. It was a NASA project. NASA decided that it didn't actually need a, basically it looks very much like the shuttle, although it's much smaller than the shuttle. It didn't need a small aerospace lander, so it got transferred to the Air Force and then to the Space Force. But the X-37s exist, they fly. We have them now. So we know how to enter the larger payload capability into the atmosphere of Titan. For this particular case, in fact, we're coming in, we're landing as if we were an airplane, but at the very last minute, in fact, we open up parachutes because we don't have a runway prepared on Titan. We need to do sort of the vertical landing onto a predetermined spot. But still, it's a problem. This is a pretty big launch vehicle. How do we fit the launch vehicle in to the limited volume? And we solved that problem using inflatable fuel tanks. You'd think, well, that's kind of a crazy idea, but in fact, there's a lot of testing being done trying to solve that exact problem, to make these basically Kevlar fiber or other fiber fuel tanks that can hold oxygen and methane. So that ends us giving us a deployable rocket. Well, it's now a 3-stage rocket. I probably won't go through the calculations on that, but we need 1 stage just to get us above the atmosphere. Then once we're above the atmosphere, a 2nd stage takes us to Titan orbit. And then once we're in Titan orbit, a 3rd stage takes us on the trajectory to go back to Earth, which I'll talk about in a second. So there's the vehicle as it's compressed compared to a typical Zamboni like you might have in your ice rink if you happen to be a National Hockey League.
Another ice scraping
So,
thing.
but there it is when it gets expanded. So it expands by not quite a factor of 3. So we can fit the compressed vehicle into that lander, get a fully deployed vehicle, and then do that launch from Titan that can take us to orbit, and then from orbit into Earth trajectory. And there just shows how everything fits inside that expanded X-37 for landing on Titan and then deploying it. Well, probably not hugely interested in the Earth return vehicle because, in fact, we just stole the Earth return vehicle from a previous project. This was used for the Stardust mission, used again for the Genesis mission. It is a high-velocity entry vehicle that can bring a sample back from orbit, or in fact from interplanetary space, to the surface of the Earth. The only complex part of this was that the scientists said, oh, by the way, you collected these samples at 91 degrees Kelvin. We don't want you to heat them up on the way home. We want them to stay at 90 degrees Kelvin. So when we get them in our lab, they're still at 90 degrees Kelvin because we don't know what chemical reactions might happen if you heat them up to the blisteringly hot temperature of, for example, room temperature. So we ended up doing that by saying, well, we'll make just a little bit more liquid oxygen while we're here. We can keep them cool in interplanetary space. Because interplanetary space, if we shield ourselves from the sun, nothing gets very hot. But when they're going in through the atmosphere and the heat shield, coming down on the parachute, well, they might heat up. So we're using the liquid oxygen that we've made as basically a giant ice cube that keeps it cool until they can be retrieved from the Earth. Well, how do we get home? Come on, isn't this gonna play? In fact, it's tricky. We don't want to use much propellant to get home. So we start out by launching from Titan into orbit around Saturn. Then we do a flyby of Titan to make a bigger orbit. Another flyby of Titan to make a bigger orbit. Yet another flyby of Titan to increase the distance from Saturn. One more to really increase the distance from Saturn. Then we fire the rockets, not to go out, but to drop in. So we drop into a very close flyby of Saturn, fire the rockets finally, and that shoots us out toward Earth. Well, that's sort of complicated. Why do we do such a complicated maneuver? Oh, come on, I want to do that again. Mostly to save fuel. When we make the very close flyby to Saturn, of course, we're going very fast. Saturn has a big gravity well. So we fire our engines when we're going at the highest speed that gives us the most efficiency, and that allows us to get back home to Earth without having to do anything like, for example, a Jupiter flyby, which would require us waiting, I think, about 10 years until Jupiter gets in the right position. So that's the phase 1 project on Titan sample return. Well, right now we're in the process of writing the proposal for phase 2. We want to take this idea and fine-tune it, see how we can do it better. Well, our first thought to do it better is literally half of that rocket stage launching us is just getting us above the Titan atmosphere. So now we're saying, well, can't we use that atmosphere instead of trying to punch through it? Let's see if we can use it. One possibility is to make a winged rocket. So instead of punching through it straight up on rocket propellant, well, let's fly like an airplane through the atmosphere. But the other possibility we're looking at is, well, why don't we just build an airplane and use the airplane to carry us up above the atmosphere and then launch the vehicle from the aircraft. A third possibility we're looking at, this is not the one that I'm advocating, but might be worth looking at, is to use that hydrogen that we've made, make a balloon, and use the balloon to loft us above the atmosphere. So we have several different possibilities for how we can use that atmosphere in order to have it on our side instead of being a drag force, just making it a more complicated mission. There's been only one other analysis of Titan sample return, and this was done about, I think 15 years ago. That one cost a lot more, and if you look at it, it ends up being a much larger, much heavier, and much more complicated mission. We could launch this mission on a Falcon Heavy, rockets that we have today. The mission that was proposed for the previous one requires the larger version of the Space Launch System, weighs almost 10 tons, landed on Titan, and we think that that was a little bit optimistic. I think it's would in fact take more. So we save a lot of mass launched from the Earth by going to the in situ propellant that we're proposing. And that pretty much covers what I have to say. We think a sample return mission from Titan would just be invaluable. It would tell us a lot about our place in the universe. We have a initial design for how we can do that using in situ propellant production, and should be feasible. And as an added feature is we're now using some of the same ideas to see if we can do a sample return from Venus. Stay tuned on that one. It's a study that we just started.
The earlier thing you did as a lander, how much chemical work can that do on studying these filaments?
How much can you do in situ with lander instruments?
Yeah.
Well, to be fair, the science instruments we're putting on landers are getting better and better, but they still don't have the very serious instruments that we have on the Earth. We don't have the capability to have NMR, nuclear magnetic resonance. transmission and scanning electron microscopy. You really need the Earth laboratories to get detailed information on the materials. You get overall information, maybe mineralogy, bulk chemistry, but to really get detailed chemical analysis, you need the labs on Earth.
Now, is the timing such that you might have some of that information before this thing gets sent up, so you know more about what's down there?
Yes, this launches after Dragonfly. So we think of Dragonfly as being our scouting mission, because it can fly around, look at many different sites, tell us which are the sites that have convenient access to water ice, because we need the water ice rocks. It'll tell us overall the characteristics of the surface. It'll tell us the overall composition. So we're really planning on Dragonfly as being our scout mission.
Dragonfly is gonna try to figure out if those water rocks are really that, and if that well.
Yeah, we're pretty sure that there are some locations that have water ice rocks. We've seen this from the infrared spectroscopy from orbit. We can see some outcrops of what seem to be pure water ice rocks. But Dragonfly will give us good on-the-ground information. It'll tell us a lot that we don't know. So far, we've seen one site on the surface of Titan, and only an area of a few tens of square meters at most of surface area. We don't know what most of the surface really looks like when we get down there.
Have we learned anything helpful from the recent sample return to not have that stuck mayonnaise jar lid problem?
Yes,
for
I
future sample returns?
certainly hope that won't be a problem with us in the future. Nobody anticipated that opening the jar was going to be the tricky part in sample return. To be fair, it would be easy enough to open it, but they wanted to open it absolutely pristine,
Sure.
so that nobody's hands were anywhere near it, no Earth atmosphere was anywhere near it. And they wanted to make sure that you couldn't just use say an electric saw that would put fragments of metal into it. You wanted to make sure that the pristine sample maintains its pristineness. But yes, I'm hoping that having had that problem once, we'll figure out how to do it a little bit better next time. Way in back, question. Oh.
That camera that took thousands of pictures of the same three water line, water ice cubes. Was that a design, was that deliberately designed that way, or was it a failure, or what?
It was just, it's a long way to go on a mission that was very mass constrained. So they figured that mostly what they're trying to do is go through the atmosphere, take pictures as you go down through the atmosphere, and successfully land and see what the surface is like. And they just didn't have the mass and the power budget to put a pan and tilt on the camera. In retrospect, you think, oh man, you should have spent the extra few $1 million to get that built and qualified. But I think the engineers at the time were mostly interested in saying, man, let's just get this to work. Let's not make it fancy.
Define in situ.
In situ means in place. So when I say in situ resources or in situ propellant, it means making propellants from the resources you find where you are, rather than bring them from Earth.
Okay.
So, sure.
Is there any geologic activity or volcanism on Titan the same way like Io has?
Yeah, is there geological activity on Titan? Mostly that's not understood, because we can only see the surface of Titan from the radar observations from Cassini, and Cassini just passed by sort of every now and then. It made a close pass by Titan. So we don't have a continuous look at the surface of Titan. Certainly we see features on the surface of Titan. We haven't seen anything like volcanoes or geysers or tectonic plates, but it's so really hard to look through the clouds. It's completely possible we may have missed a lot of features. There's certainly always been surprises every time we've looked at moons in closer detail. Sure.
Is Dragonfly a go? I mean, that's an actual project that's slated to launch.
Dragonfly passed their design review.
Okay.
It is go. It's always subject, of course, to budget issues.
Understood, but
So
like
it could be
then
canceled, but right now it is a go project. They're working as hard as they can to make that launch date.
the further future submarine and the sample return,
These are
less
so far
certain?
design projects.
yeah, okay.
We'll see how Dragonfly goes. If Dragonfly tells us it's exciting, we'll have a lot of people saying, "Oh, we got to take the next step."
Is ion propulsion out of the picture for
No, we
part
use-
of the return? Or-
We use ion propulsion for a lot of things. Ion propulsion is superb at the inner solar system because you can do solar-powered ion propulsion, solar electric propulsion. And we've done a lot of studies of that. Unfortunately, the solar intensity at Saturn is way under 1%
Okay.
of the intensity here. So
So it'd
solar
be no
electric
help trying to
propulsion is
improve
hard.
return.
You'd have to have huge solar arrays. Alternatively, however, nuclear electric propulsion, if you have a nuclear power plant, would really help out in the outer solar system. We don't really have that ready yet.
Okay.
Hold on, cross your fingers for technology, and maybe we'll get the nuclear reactors working in space and we can start thinking about nuclear electric propulsion. We have some really nice designs for that,
Cool.
but at the moment, it's beyond the technologies we have.
What material is the lander made of?
Titan's not a really hard problem. You have a lot of materials problems when you get hot, but cold materials are not a big deal.
Are they alloys of some sort?
It'll probably be realistically aluminum alloys because aluminum alloys are so simple. There's also a lot of composites, mostly carbon fiber, in the Dragonfly, because Dragonfly needs to be lightweight. Right? The lighter it is, the easier it is to fly. So there's a lot of carbon composite graphite in Dragonfly, but conventional materials pretty much work out at Saturn. Once you start going toward Venus, it's a whole different
What
ballgame.
ship are they considering to launch it? Falcon?
I'm not sure if they have made the final choice on the launch vehicle. I think it's designed to be able to launch on any of the moderately heavy launch vehicles, Falcon or possibly Vulcan, but I shouldn't say there because I don't actually know if they've even picked a launch vehicle yet. Usually the launch vehicle actually comes late in the process.
We certainly have the technology there, though. They don't have to design a new vehicle.
We don't have to design a new vehicle. We don't have, for any of these missions, we've been designing to existing vehicles. And that's another wild card. If some of the big launch vehicles that are being proposed get made, we can start thinking of very big missions. There's some pretty massive launch vehicles that are possible in the future.
Bigger than the Heavy Falcon?
The Starship is a heavy class launch vehicle, Saturn V class. The SLS Block 2 is a heavy launch vehicle, again, a Saturn V class launch vehicle. So there's the possibility of some very capable vehicles coming in the future. We just don't design to them because they don't really have detailed specifications yet. But boy, hang on another couple of years and it may be a whole different ballgame for how much mass we can launch to orbit.
I asked about the, currents inside the lakes. What about air? Just winds and stuff like that. Is this another Mars dust storm type place, or is this?
Yeah, people are again modeling the atmosphere of Titan. There's a lot of models of the atmospheric circulation, not a whole lot of ground truth on that. We did our designs for the worst case believed wind velocities on Titan to make sure, for among other things, that once we erect our vehicle, get ready to launch it, that there's not going to be a windstorm that'll blow us over.
I was thinking about the aspect too, of like dragonfly, trying to fly around.
Yeah.
Yeah, the dense air is gonna be nice to make it fly easier, but the dense air
Yeah.
will also be worse if it's moving around a lot.
Yeah, they're designed for worst case scenarios, so it should be okay. But again, you always learn different things when you're actually on the ground. But with luck, things will be better and not worse than believed.
Very cool.
Although
all right, one more.
This is kind of on a different subject. Have you or anybody at Glenn been involved in the Europa Clipper mission?
We had some involvement in Europa very early in the design process. We were looking at multiple options for how to get radar imagery of the ice. But once JPL was selected as the prime contractor for Europa Clipper, it's their baby now. So they're working on it, and it's also a mission that's planned to go, but we don't have any major role in that mission now. Okay.
All right, thank you very much, Dr. Landis, everybody.